Well, welcome back, everybody. Uh, that's good. I didn't scare everybody away. I still got about most of you came back. um, Let me do a couple of things here. I got a couple more people showing up, so give me a minute so I can let them in. All right. Okay. Well, let us begin. Now, I understand we spend a lot of hours here, and there's online. It's quite a bit of online instruction. It's kind of a challenge for everybody. I got my kids and little going through online. They're having their challenges, so trying to make it as interesting as possible. Obviously, if we were face to face, it'd be a totally different ball game. But if you have any suggestions that would make it a little more, I mean, I have a couple of things I can do, but I can't. I can't. I've been told to stay out of the kitchen, so I was going to do some experiments, and they're like, no, something I could do at normally I could do when we're doing face to face. So anyway, um, let me continue with where we started. Anybody have any questions? Does everybody understand where they can get their textbook? A quick word about that. The textbook was created by the Maricopa Community College faculty. The purpose of that was to make it free for you. Okay. Now, some people do like a textbook, and I did offer the what's called OER textbook that you can download. I believe that one's free, but keep in mind that that textbook, our textbook is lined up with our schedule. Now the topics are the same, okay? It's just they're going to be out of order. So if you need a regular quote textbook, you can take that one downloaded. It'll be PDF also, and so you're back to square one. Or any general chemistry textbook that you can find will be fine if you need to have more information about a topic. We're trying to help save money with respect to your costs because a lot of us here, you know, I remember spending $200-300 for a textbook that I never used again, and that's really cost that you can use someplace else for other things. So we're trying our best to minimize the cost for you. So it's all the textbooks. In fact, let me go to that screen and I will uh, go through there because I want to make sure that everyone understands where they can get their information because I know it may be redundant. And if you're familiar with it, that's good. But I've had um, situations where people have asked, toward the end of the semester, where is my textbook and where's this and where's that? As I mentioned in the beginning, we have everything that you need is set up to be in modules. Okay. And so um, you have a welcome module, first steps, and that's the first steps is something that SCC put together. Additional chemistry resources, that is something that I put in to give you additional resources. Do look at those. I included in here a module that has all the PowerPoint PDF files. I created one up PDF files of all the PowerPoint slides. Now, some slides I may use, some I do not, but you got them all there in PDF format. There's a module for all the chemistry labs. Everything you need, I shouldn't say you ever need, everything you need should be in each individual lab. So you shouldn't have to worry about needing additional information. Every chapter has multiple things. Is one, you have an overview, which is a good study guide with respect to that particular chapter because it tells you what we're going to cover, what are the topics, and it's something that's a good resource to say, okay, I'm going to get ready for the first exam, which is coming up here fairly soon. That's a good additional resource as a study guide. You have the textbook, okay, and it's labeled chapter X, whatever chapter it is, OER, which is open resource, okay, and then PDF. So every chapter, that is your textbook for that particular chapter. Then I talked about the videos, two types of videos. This first set that you find, this link sends you back to the website. Those are videos that were created by another professor concerning this particular topic. That professor is Dr. Kim. Uh, uh, the same information she covers, I cover. Now the videos I have after we're done talking about whatever chapters we're doing, I upload them to my YouTube channel. You have a link in the far left, YouTube recordings, that you can access the videos concerning the Zoom sessions. So here's another resource for you, having another person talking to you about the same topics that I will talk to you about. And so every chapter has a video. The worksheet, there's a worksheet there, which is a list of problems for that particular chapter. And there's your activity, online activity, and your home, which another point about Canvas. Canvas treats everything online as a quiz, okay? And so right now, when there's questions and you send me an email, you ask me about a quiz, I'm pretty sure you're either in chapter 1 or one of the activities. I can find it. But as we progress, some of you are going ahead, which is good. I need to know which activity or homework you're talking about, or lab, because even the labs, Canvas treats them as a quiz. So if you just tell me quiz, I don't know which one it is. So I'll have to email you back which one are you talking about. So let me know when you have a question. If it's a homework, what homework number, what question number, or activity, what question and activity. If it's a lab, let me know what lab you have a question about. And that way I can get to your answer as quickly as I can. Okay. All right. So again, everything's there for everything you need is broken up in modules for every chapter. So you should have access to it. There is a practice extra credit. Some of you haven't done it. It's extra credit. I don't understand it. It's an easy 5 points. Okay. The point of that was to check the lockdown browser. Now, a word about the lockdown browser. It is only used for the exams. So it's not used for the homeworks. It's not used for the lab. Let me restate that. It's only used for the exams. It's not used for the labs. It's not used for the homework or the activities. Okay. And all that does is just flag when you get out of the browser, locks your browser. And if you ever stop, it just flags. It tells me that you are someplace else. So if you have to get, you're doing homework. Okay. I said questions that you did the extra credit, but it didn't work. Oh, it didn't work. Okay. All right. Let me find out about it. See what's going on. There's some instructions for the lockdown browser. It works best. In fact, Canvas, I'm told from Canvas Tech Support tells me that the best browser for Canvas is Chrome, the latest version of Chrome. So if you're not using that, you might want to maybe try it, update it, make sure you got the latest version, and see if that works for you. Okay. So yes, let's. I will look into why that's not working for you. I'll find out. So check the lockdown browser. Let me know when that happens, and then I will give you your extra credit. Okay, iPad. So you're using an iPad, Kathleen? Okay. With respect to images, it's another good point. Canvas is having some challenges here this past couple of weeks. And I don't know what's going on. I got letters or emails sent out to tech support. They tell me they're working on it, but one aspect was images on the question. Sometimes you see them, sometimes you don't. If you don't see an image, don't worry about it. Let me know. I will definitely give you credit because it could be a fluke with something going on with Canvas at that point in time. So if you don't see an image, let me know. We're working through it, at least tech support is, figure out why it happens sometimes, and other times it's great. Okay. With respect to Mac, I don't know about Mac laptops that much. I'm a Windows kind of guy, but I will research it and I'll give them I'll give tech support an email, ask them about the Mac. Okay. All right. So everything you need is in modules. So you shouldn't be, hopefully not, hopefully you should not have to go search for things. Everything's given to you there. Okay. Now, with respect to email, you send me the email through Canvas email. You find the far left, the inbox, create an email and go from there. Okay. We're going to use Canvas first for email. That's the quote official way of conversing with students. If for some reason Canvas is not working, then by all means use my edu email address. Okay. Any other questions? All right. Well, let us proceed there, because we were talking about, we ended up in we're still in chapter 1. We were on page 21 according to my notes. We were talking about chemical changes versus physical changes. All right. And which normally when we do mention chemical changes, we are talking about chemical reactions. Okay. Chemical reactions. Yeah. Oh, a question about the lab. The labs are on your time. Okay. So the lectures are live lectures, but the labs are classified as on your time. I set them up so you have access to them. The first lab obviously is due today, and you're going to have one every week starting today. Okay. All right, so we're talking about chemical reactions or chemical changes, aka chemical reactions. A good example is burning of fuel, gasoline. This is a very general reaction, general reactants. To the left of the arrow, you'll see CXHX. That is a general formula for what we call a hydrocarbon. Okay, hydrocarbon. And when you drove your vehicle today, that's what you did. You were burning. You did a combustion reaction. In fact, that is one of the reactions that we'll be talking about when we get down to reactions. There's only 6. One of them is here, combustion. All right. So how do we look at something and say, we got a chemical reaction? What are indicators that something happened chemically? There's a multiple of them. Okay. Obviously, the one that burns, think of it in terms of when you get a chemical reaction, you change whatever you're doing with the reactant is changed completely to another product, another material. So when we burn something, obviously it's no longer the material. The fuel we burn is now carbon dioxide and water, for example. That piece of wood burns, we got ashes, has created something else. Rusting is another example. Okay, you have metal that rusts, reacting with moisture and oxygen in the atmosphere and creating a new counterpart. Sometimes you get release of bubbles, what we call fizzing, without any heat. A good example of this would be Alka-Seltzer. You take an Alka-Seltzer tab, you throw it in the water, and it bubbles. Okay, and it bubbles, and it's all, I often wonder why the Alka-Seltzer people put in that material, because it's not. What's happening there is you're getting maybe citric acid and sodium bicarb in the tablet. And once it dissolves, those two react to form carbon dioxide. It's like getting baking soda and vinegar, you get bubbling action. So in Alka-Seltzer, the carbon dioxide is not really doing anything medicinally that I'm aware of, but it carbonates your drink there. So release of bubbles without heat. Formation of a solid. You might get 2 liquids, they're clear, or maybe even colored, and you mix them together and you get a precipitate. If it precipitates, a solid's formed, that is a very good indication that a reaction has proceeded. Okay. Things like release of heat and light. Classic example, you go to a CVS pharmacy or any pharmacy, you buy yourself a cold pack or a hot pack. You take that pack, you smack it, it gets hot or it gets cold, depending which one you purchase. Okay. That's a good indication that we got a chemical reaction occurring. Okay, release of heat, okay, or the taking in of heat to get cold. Light, the glow tubes, those glow things that you take, you break them. Okay, there's a chemical inside in the glass container. You break the tube, and then after a while, it lights up. There's a chemical reaction that occurs there. One of the products that is emitted is light in that process. Glowworms, that's what's happening in their tail. There's a chemical reaction occurring in their tail to release that light. Change of color. Okay, something is blue, maybe it goes clear, or any color, any change of color, or something's clear, it goes to some color. Odor. You get two reactants, you put them together, it may get a product that smells real bad, or you may get a product that smells good. A lot of them, wintergreen, banana oil, a lot of good smelling stuff are the result of two reactants that don't smell too good, but when you put them together, you make a nice smelling material. Okay. Here's a classic example of a chemical reaction. I really like this one here because it really demonstrates the power of electrons, the power of electrons. When we have, if you take sodium metal, which has a symbol N lowercase a, okay, and it's a solid. We're going to learn about this here pretty soon. In room temperature, it's a solid. When we reacted with Cl2, there's a subscript 2, which tells us there's 2 chlorine atoms. So it's a diatomic element. This is called chlorine, INE. You're familiar with sodium, for example, chloride, IDE. There's a reason why the name gets changed, okay? But both of these reactants, the sodium, which is a metal, shiny, this one's soft. Chlorine, very reactive. If you were to put sodium metal in your mouth, it would erupt, explode with the moisture in your mouth, generate lots of heat, and probably ignite the hydrogen that's given off and explode. Okay, very, very impressive reaction with sodium metal. Chlorine, Cl2, is a gas, and guess what? It is a poison. Okay, if you were to inhale that thing, it would give you all kinds of trouble. A lot of the municipalities around here, the water treatment plants, not a lot of them, some use chlorine to treat the bacteria. So if you live nearby one of these, and someday you look in that direction, you got a yellowish pot of smoke coming out, get up one quick. They got a leak. Okay, chlorine. Very poisonous. Those two react together and they produce NaCl. NaCl is what you put on your French fries, sodium chloride. Not as hazardous, not as dangerous. And the only difference, the only thing that happened here, one tiny electron from sodium got transferred to the chlorine to create the sodium chloride, a little electron to produce something that is not hazardous at all, unless you got blood pressure problems and you stay away from sodium. Okay, it's analogous to plucking a hair out of your head and you generally create totally somebody new, Dr. Jekyll, Mr. Hyde kind of example, and a little electron. Okay, so how do we define now? Given these reactions, understand you're not familiar with the reactions. It's okay. You will eventually, with time, recognize what we're going to put here. But the point of this exercise is to analyze that reaction, see similarities, things that are not similar, and deduce from it, either we got a physical change or a chemical change, okay? And that's the exercise here. So take number one. We have this chemical. It's got nitrogen, it's got hydrogen. In fact, it's got 3 of them. Notice it's got a subscript. We're going to learn that the subscripts for these chemicals that we put together are etched in stone. We don't ever change those. Once we put them together, we're going to learn how to put together the correct number of subscripts. but that is the formula of the compound. It doesn't change. Now we can put a number in front of it, and we call that a coefficient, like a number 2. I put a 2 here in front of NH3. I can put as many numbers as I want up front, but I cannot change that subscript, okay? Now, the other thing you can take away from that, you got NH3, so you got a chemical of some sort, some molecule, some compound, because I got 2 different elements. I got a nitrogen and a hydrogen, hence it's called a compound. Then in parentheses, I have listed its physical property. It's a gas. Okay, remember gas, liquid, and solid, G, L, and S. Then I have the arrow, which tells me something happened. It's going from point A to point B. And I look to the right of the arrow. So to the left of the arrow are the reactants, and to the right of the arrow are the products. And I analyze the products, and guess what? Structurally, it's still NH3 as it was in the product stage. So what you can deduce from that is that chemically, physically, nothing happened to the molecule. Okay, it's still the same. The only thing that's changed is, in parentheses, you have an L, which tells you it went to the liquid state. Okay. Now, so that from that information, you can deduce that I have a physical change. Okay. Now, FYI, NH3 is probably something you smelled someplace somewhere. That is the formula for ammonia. If you have a cleanser, that's what you're smelling, NH3, like a window cleaner or some sort. Also with dirty diapers, that's what you're smelling. So let's take a look at number 2. Do a similar analysis, okay? We're going to break it down here. We're going to figure out, okay, what's going on here? Well, I still got the same formula, NH3, okay? And it's in gas form, but something's different. When I look at the reactant side, I got a plus symbol, okay? I got a plus symbol. That should tell you something right there. If I got a plus symbol, that means I made 2 products. I got something to the left and something to the right of the products. That also infers that I have totally broken down NH3. And that's what's happened here. In this example, NH3 was broken up to form N2, which is nitrogen gas. Notice it's a subscript. It's another. We're going to learn that there are 7 elements that do not exist by themselves. They have to exist with another element of itself. We call that diatomic elements. Nitrogen is the first example. The other example of a diatomic element is hydrogen gas. It doesn't exist. It can't exist here on Earth. Let me qualify that. Here on Earth, it does not exist by itself. And so it's diatomic. So in here, it produced 2 gases, ammonia. Something happened to the ammonia to produce nitrogen and hydrogen, okay? So that in itself tells you I got a chemical reaction, because remember, in a chemical reaction, I have totally destroyed the reactant to form something new. Notice the coefficients in front, something to pick up on now. I mentioned the subscripts we leave alone. Okay, they're etched in stone, because we're going to learn that when we write formulas for chemicals, they come together with whole numbers of elements, either 1 to 1, 1 to 2, 1 to 3, 3 to 3, but they're whole numbers. Those are the subscripts. Okay, we don't change those. The big number in front of the molecule is called the coefficient. We can change that number any number of times that we need to. Okay, and we're going to do that for a reason, because we're going to balance equations. And so the second one indicates that you have a chemical change, okay? Because we have created 2 new products. Now let's take a look at the third one. We have H2O2. At first glance, you might think, that's similar to water, right? H2O, water. But the difference is it's got 2 oxygens. We look at the products. Guess what happened again? Look at that. We got the plus. That means we got 2 products again. In this case, we made hydrogen again, diatomic, and this time we made oxygen. Notice oxygen has a subscript too. Okay, so right now you've been introduced to 3 diatomic elements: nitrogen, hydrogen, and oxygen. I understand you don't know what this is right now, but guaranteed you used it someplace. If you ever cut your finger and you took some of this, you probably applied some hydrogen peroxide. Or if you colored your hair, you probably used some hydrogen peroxide. That is the formula for hydrogen peroxide. And again, number 3, the fact that we made 2 products tells us we got a chemical change. Number 4, again, we got H2O2 in the liquid stage. And if we look over to the product side, nothing's happened chemically to the reactant. It's still H2O2. The only difference that we can see, we got a liquid, starts off in the liquid, and it becomes a solid after, okay? So that's analogous to taking water and freezing it. It went from liquid water to solid water. It's still H2O, okay? So here we got a physical change. And then finally, we have this compound. I know you don't know what it is, but if you refresh your memory from what I said earlier, when I said chemical reaction, I said combustion of a hydrocarbon. First of all, there's nothing but carbon, which has the symbol C, and H, hydro or hydrogen. That is called, when a molecule only has carbon and hydrogen, the general name for it, the carte blanche name, is hydrocarbon. This is an example of a hydrocarbon. Okay. So we go here and you look again at the reactants, and guess what? Nothing happened to it as a product side. So again, we have a physical change because again, it went from a liquid to a gas. And that's analogous to boiling water. Okay. That, for example, that formula there, that's a formula for what is called benzene. Okay, that's not important right now. We're not going to talk much about them. It's just a hydrocarbon. Benzene is also is a carcinogen, causes cancer, not a good chemical. And so first one was a physical change. Okay, no change to the reactant as far as structurally. We still have NH3 reactant side, NH3 in the product side. Number 2, it's an example of a chemical change. We took NH3 and we totally broke it down. We broke it down to its elements. They broke it down to nitrogen and hydrogen. Okay. Let me stop here for a second and just talk to you brief. You know, you might wonder, why do we put coefficients in front? We got 2 NH3s and then we got 1 nitrogen. There's no number in front of it. It's understood to be 1, just like in math and algebra. And then 3, we have 3 in front of H2 hydrogen. So that means we have a total of 6 hydrogen atoms. Okay. In NH3, right here, 2 times 3, we got 6 hydrogen atoms. We have to balance chemical reactions. And one of the rules, the laws of chemical and physics is the conservation of matter. If I start off with X number of elements as a reactant, I'm going to have the same number as a product. Okay. All right. Next one, number 3, another example of a chemical change. We broke down H2O2. And number 4 would be a physical change. Number 5, again, a physical change. Okay. And so in this exercise here, granted, we don't know what the chemicals are. The point is to do an analysis on what you're given and determine whether you have a physical or a chemical change. Okay. Now, let's talk about elements, compounds, and mixtures. Okay. Elements, we have 118 elements. Now, if you haven't done so, let me see, where's it? Say, if you've not done so yet, do download the periodic table, okay? I'm going to make reference to this periodic table numerous times. On this periodic table, you're going to be able to find out a ton of information concerning all the elements. There's 118 elements. And if you look at number 118, bottom right corner, they have some generic names right now, symbols, UUO. Those have been found. They're officially been named. So this periodic table hasn't been updated yet, but there is 118. The last three to fill up that table were, I believe, 2015, 2016, they were actually found. Okay. Other information from the periodic table, bottom left corner is what we call polyatomic ions. Again, we'll be making reference to it. And then down in the bottom right corner, another table called solubility rules. We're going to be able to look at compounds and determine if, in fact, they're soluble in water or not. And then one last table is called activity series. There's some reactions that we're going to use that series to determine and predict the products of a reaction. Okay, so a lot of information there that you need to really download that thing and have it by your side. We're making a lot of references to it. Okay, so we're going to talk about an element. There's 118. Can't break it down any further. If we do, we start talking about subatomic particles and what the atoms are made up of. So we get the element, then we have compounds. Now, how do we define a compound? A compound is a combination of at the minimum, two different atoms bonded together. Okay. And if we can take that and we break it down further, we break it down to the elements. A good example is a previous example here where we took, let me go back up for a second. Where we took number 2, NH3 ammonia, and we broke it down to the elements, nitrogen and hydrogen. You can do the same thing with water. We take water, we hit it with some electricity, we break it down to hydrogen and hydrogen and oxygen. So a compound can be broken down further through the elements. And then, of course, we've got mixtures, anything that's pure, basically it's the same material of whatever we're looking at. It could be a pure element. It could be a pure compound. Okay. Or a mixture. Pretty self-explanatory with respect to pure and mixture. Diagram here. Now, we're going to make reference to a lot of these diagrams to depict a situation where there's solid, liquid, or gas. But if we look at the shapes here, let's take, for example, we go from matter. We take matter, top of the flow chart, go to the right to mixture. Okay. If we look at the mixture here, obviously we can see that we have two different, let me circle them, two different elements. We have these dark spheres that are highlighted, okay? And then we have these that are kind of put together, they're combined together side by side. That's a good example of these diatomic elements I was talking about, like oxygen and nitrogen and hydrogen. They're put together like this. They're shown in this manner, and they are the same shape and the same color. That's an indication that they are the same element. And so that you can take away from that is that I have a diatomic element. Then I got the dark spheres that are all by themselves. So obviously I got a mixture here of two elements. One of them has to be diatomic. If I look to the right, okay, I got three of them, three elements. I got this kind of magenta, green color, a red color sphere, and the dark one. So again, that would indicate a mixture of three different elements. When we go to the pure substances on the left of this flow chart, if we go down the side of elements, we have two types of elements. They're all by themselves, like the circular sphere, all by themselves, just pure. A good example would be like neon gas, to give you an example here. Or it could be diatomic, where they're shown next to each other, okay? The diatomic elements, a lot of times you use the name molecule. This is a molecule hydrogen, this is a molecule nitrogen, and so forth. With respect to compounds, remember, by definition of a compound is a combination of two different elements. Now, we will learn that when we start looking at formulas of compounds, there will always be one element that is a central atom, and everything else is bonded around it. So here, this could be a depiction of hydrogen of water, H2O, where you have the central atom, which is oxygen, shown here in red color. And then the smaller yellow spheres can represent hydrogen. Okay. They are bonded to the central atom. You will always be told who the central atom is. And we're going to use that a lot when we actually be able to look at uh, uh, formulas and determine the structure and so forth and geometry. But you have to be told what the central atom is. And then we have another one here where we have two different spheres, colors put together side by side. Now, of all the chemicals in the world, there are two types of bonds. And there's a good example here. The sodium chloride on the right is basically an example of this. These are ionic compounds, and we call them ionic for a reason. We'll learn about that here in a bit. But they are like two magnets. These ionic compounds, one has a full positive and one has a full negative charge, and they come together like two magnets. Sodium chloride is a classic example of that. H2O, totally different. The bond there is essentially shared. So the bond between the hydrogen and oxygens, their electrons are sharing them, and we form a very strong bond. Okay. So that is your introduction to chemical bonding. You're going to learn that of all the chemical bonds, there's only two types of chemical bonds. All right, so let us continue. Mixtures. Well, there's all kinds of mixtures out there. Obviously, metal alloys are a classic example of a mixture. The gold in your jewelry that you're wearing, your ring, that's a mixture. Pure gold by itself is not very good to function as a ring because it's very soft and not very sturdy, crush on you. Brass is a mixture of zinc and copper. And stainless steel is not just iron; it's a mixture of carbon and some other metals in there. So they're mixtures. Sand, granite, a good example of mixtures. Tap water, very classic example of a mixture because the tap water has a lot of stuff dissolved in it, not pure. And the air around us is another example. It's a mixture of gases, nitrogen, oxygen, hydrogen. There's a whole bunch of them. Pure material. Well, we can get sodium chloride, a good old table salt. A word about the term salt. I know probably up to this point, when you think of salt, you automatically think of table salt. But with respect to chemistry, salt is much more than just table salt, okay? Earlier I said there's two types of bonds. One of them is called ionic bond. We're going to learn how to determine what an ionic bond is. But all ionic bonds are salts, and that's a combination of what we call a metal and a non-metal. Sodium chloride, sodium is a metal, the chloride is a non-metal. Okay? So when we use the term salt, just don't think about table salt. Think about a lot bigger. I'm having a senior moment here. Salts are a lot more. They're a lot more in number than just table salt, sodium chloride. A diamond, pure diamond, is made up of nothing but carbon. Now think about this for a moment. Think of what I'm just telling you here. Diamond is the hardest thing on earth. Okay. And it's made up of an organic compound, or an organic element, carbon. Another example of this would be graphite. If you're not familiar with graphite, graphite is a dry lubricant, has some carbon in it, very slippery, nowhere near the hardness of a diamond. And you might think, well, wait a minute here. I got carbon here in the graphite, which is real slippery, and then a carbon in a diamond that we use in drill bits and so forth because they're so tough. Okay. Why is that? Well, it's the way they're put together relative to each other. You know, their structure and how they're put together that gives them the strength. Another example would be polystyrene. Polystyrene, we're all familiar with polystyrene. We use them in cups, right? But the polystyrene we use is very soft. I can crush that polystyrene cup with no problem. I can dissolve it in acetone with no problem. But if I adjust the structure of polystyrene, which is made up of nothing but carbon and hydrogen, a hydrocarbon, I can make material that's strong enough to make buildings with, you know, and just a matter of how molecules are put together relative to each other. All right, distilled water, that's a pure substance. Distilled water is nothing more than taking tap water and heating it, boiling it, and then condensing it into a what do you call it, a condenser, just like making the steel, if you will, and collecting the water. And now you got pure water. Okay. And then mercury, a lot of the metals, you can put them in pure form, elemental, a lot of the elements. All right. So a classic diagram that you'll be seeing at length would be as follows. The block on the left represents an element, specifically an diatomic element. The block in the center represents a compound. Okay, compound by definition, two or more different elements. It looks like the white color sphere is the central atom, and the two darker ones are bonded toward the central atom. And then if you look at the last one, obviously you can see you got a mixture of a compound, an element, two different elements. Okay. So you might see something like this, where you kind of define this. Is this an element, compound, or a mixture? If we look at number 8, oh, it's an element, specifically a diatomic element. Okay. B will be a good example of a compound because you got the dark sphere, which looks like the central atom, and the two white ones bonded around it, 3 of them bonded around the central atom. That would represent a compound. Number C looks like elements, specifically a mixture because you got 2 different ones. D looks like, again, an element, pure, there's nothing else there except whatever the dark spheres would represent. E would be an example of a compound, again, pure. F would be a mixture again of a compound and a diatomic element, okay? And then G is would represent an element, mixture, and compound. And then finally, H would represent an element. Now, of these, I can also deduce that H probably, more than likely, is a solid. Its physical state will be solid because of the way they're ordered and structured. The other ones could be gases, could be liquids. It's hard to say, but definitely they're not solids. Okay, just based on the way they're put together relative to each other. All right, well, let's briefly talk about elements. Each element has a unique name, a unique symbol, and a unique number, okay? And if we go back to the periodic table for a second, you can see we got 118 of them. And then each one has a letter. You'll see the number, the letter, the symbol, which consists of a uppercase letter. And if it's 2 letters, the first one is uppercase, the second one is always lowercase, okay? And above each symbol, you have a number. That number is going to give us a lot of information, okay? As we start learning about these elements and how they're put together. But I can tell you right now, what defines an element is its proton. And so when I take a proton, one proton, I have created hydrogen. If I add another proton, guess what? I create a helium, number 2. And if I keep adding protons until I get to number 18, I made element number 18, 118, all totally with different properties. And so, different elements, okay? Different type of matter. It's analogous to uh, these toys that you can put together. You get little blocks of plastic and you can create an infinite number of different shapes. And they're all made up of the same little block. Okay, so protons are define what a proton is, to define what an element is. Oh, question was asked, with the table, would it ever be complete, or would we keep adding? No, well, right now it's complete at 118, okay? 118. And they're already working on 119, and we're going to learn where 119 might go, because it predicts this periodic table is full now, but there was a point in time where it wasn't full. And it predicted where elements should be. And sure enough, scientists went after it and found them based on prediction. And it's based, this whole thing is set up based on number of protons, number of electrons. Yeah. Up from number 92 forward, 92 forward are all man-made. 92 back are natural made. Okay, and they're working on making more of them. All right, let me go back. So each one has their own unique name, has their own unique symbol, and their number. They have a letter and it's a symbol. Some of them have one letter, which is capitalized. I repeat, always capitalized. If they have a second letter, that second letter is lowercase. I repeat, always lowercase. For example, cobalt, its symbol is C, capital C, lowercase o, which if you were to write uppercase O, you created a whole new compound, because uppercase C, uppercase O is the formula for carbon monoxide, okay? Not cobalt. So be careful in how you write the symbols. C, lowercase a, is calcium. He is helium. All right. Now, most of these elements do have English names. H for hydrogen, O for oxygen, H and He for helium. But there's a lot of them that have names that are derived from Latin. PB, plumbum, meaning waterworks. AU is gold, okay, meaning the golden dawn. So be familiar with right now with the first 20 elements. So let's go to the first 20 for right now, and we'll get the name of them. So number 1, upper left corner, is H for hydrogen, okay? Let me zoom up a little bit. Now we go across. Now notice what we have here. Let me a couple of things that you need to be familiar with, because we're going to use them quite a bit. We have the columns 1A, 2A, and then we got to shoot across to 3A, 4A, 5A, 6A. We're using the Roman numeral. They use a Roman numeral numbering until we're across all the way to 8A, okay? And so we start with number 1, which is hydrogen. Then we shoot across all the way to 8A, where we get to He, which is helium. And then we go back to number 3, which is in the column 1A, number 3, and I, which is lithium. Right next to it is Be, which is beryllium. And then we shoot across to column 3A for B, which is boron, C for carbon. Next is N for nitrogen, O for oxygen, that's number 8. Number 9 is F for fluorine. And then we're back to number 10 for neon. Then we go back to group 1 for number 11 for Na, which is sodium or natrium, but we call it sodium. Mg, number 12, is magnesium. And then we shoot across to column 3A again, and we meet up with good old Al, aluminum, okay? And then number 14, which is a very important element, otherwise our electronic devices wouldn't be functioning very well. Si for silicon, and then P for phosphorus, S for sulfur. 17 is chlorine. Now notice something here. Let me change the color here for a second. The naming of these guys, very important, but number 7, I'll come back to this. Number 7 is chlorine, INE. Earlier, we had the example of sodium and chlorine as a reactant to form sodium chloride. There's a difference between INE, chlorine, and chloride, IDE, okay? Keep that in mind, they're not the same. And then number 18, which is AR, which is argon. And then we shoot across to number 19 with K for potassium, or kalium, or potassium. And then Ca, finally, calcium, okay? We're all familiar with calcium. Calcium is very important mineral for bone formation, but these are elements, and this calcium is not what you're ingesting, okay? The calcium that you are ingesting are calciums that have lost electrons, and they're what we call ions. All right, so those are the first 20 that you want to be familiar with. And then on top of that, we have some other ones that we're going to be adding as we progress. Ag for silver, Au for gold, we talked about that, Pb for lead, Br for bromine. Notice bromine versus chlorine, okay, and fluorine. Okay, those are the elements. INE is the element, and then I for iodine, okay, and then Hg for mercury. All right, so let's briefly talk about the physical states of these elements. When we talk about the physical states, we had to define what temperature we're talking about, because obviously the physical states on the surface of the moon would be different than here on Earth. So by definition, when we talk about the properties, physical properties, we're talking about 25 degrees Celsius, and that is roughly room temperature, okay? Right now in your room. And 1 atmospheric pressure, we right now are approximately 1 atmospheric pressure, okay? Of the 118 elements, only 2 of them are liquids. One is mercury, and the other one is bromine, okay? Of those, we have hydrogen. Notice they're all diatomic because they're the subscript. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and what we call noble gases, okay? Noble gases, let me go back to the periodic table, is that one in group 8A, Roman numeral 8A. And that is these folks right here, okay? And they're there for a reason. Those guys are called noble gases. They're given the name noble because they are unreactive, okay? They are inert because they have fulfilled, from an electron standpoint, a certain number of electrons. And because of that, they are not very reactive, okay? So those noble gases, we have 1, 2, 3, 4, 5, 6, and 7 noble gases, okay? 7, 8, 9, 10, 11, 12. There are 12 noble gases. Let me restate that. There are 12 elements that are gases of the 118. Okay. 12 of them. And so that leaves how many? 106, right? Elements. And of the 106, 2 of them are liquids, mercury and bromine. So we have how many elements are solids? We might do the math and see the majority of them are solids. Okay. Yeah, I think we got 104. Check my math. All right. This flow chart here, excuse me, this periodic table here summarizes it for you. And so what we have, we put it in red, the 2 liquids are right here, bromine and mercury. Okay. The ones in yellow are the gases. And the ones in blue, light blue, are solids. Okay. So at a glance, using the periodic table, you can very quickly determine the physical state of the element given your periodic table. Okay. Now, I talked earlier about diatomic. There's a little something here to help you out to remember. There's only 7 of the 117 elements there. Only 7 of them are diatomic. They require 2. They need a buddy of themselves to exist here at 25 degrees in 1 atmosphere. And we use this, you can use this have no fear of ice cold beverage to help you out. Where the H of have is for hydrogen. The N in no is for nitrogen. The F in fear is for fluorine. The O in of is for oxygen. The I is for iodine. The C is for chlorine, not carbon, chlorine. And the B is for bromine. Okay. Of these diatomic elements, bromine is a liquid, iodine is a solid, and all the rest of them are gases. Okay. This is the type of information you eventually really need to know. Why? Because you may get a problem where a reaction is given to you in words. Like earlier we did the reaction of sodium in the presence of chlorine gives you sodium chloride. Taking those words, you convert that into a chemical reaction. Na is a solid plus Cl2 is a gas to give us NaCl. Sodium chloride is a solid. Okay. So you learn the physical state of these elements. You don't have to memorize them all. Just know a couple of them here: the yellow and the liquids, and the rest are solids. So you can, at a glance, determine just by finding this position on a periodic table what is the physical state at 25 degrees in 1 atmosphere. Be aware of which ones are diatomic. Okay. Now there's 118 elements, but there's only 3 types. There's 1 type. 1 type is called metals. Okay. The other type are classified as nonmetals. And then what we have is called semi-metals. Now, what do we mean by semi-metals? Well, a classic example of that is a mule. Okay, you're like, what does a mule got to do with anything? Well, let me ask you this: how are mules produced? Please don't say from other mules because they're sterile. Okay. A donkey and a horse. That is correct, Thomas. So a mule is a combination of a donkey and a horse, and therefore they have the attributes of a horse and the attributes of a donkey. Okay, and that is what a semi-metal is. They have attributes of metals and attributes of non-metals. Now, the best way to show you this is to use the periodic table. Now, what we have here in pink are what it looks pink. Yeah, it is a kind of a pink color. on my screen are all the nonmetals. The blue is the metals, and the yellow is the semi-metals. Now, the quick way you may notice something. Let me share with you the periodic table. Most periodic tables have this stair step. Okay, and the stair step allows you to determine the semi-metals. Anything to the left are metals, anything to the right of that are non-metals. So if you start off with boron number 5, right here, and you go right across the silicon number 14, and then from there you go straight down, and then across, and then straight down, and then to the right, and then down, to the right, and then down. Okay, those are the semi-metals. And everything to the right of those semi-metals are non-metals. Carbon, nitrogen, oxygen, fluorine, non-metals. Don't forget the other non-metal way over in the far left of the periodic table, hydrogen. Hydrogen's a non-metal. Okay, that means that everything else now are metals. Okay, now this is how we classify what type of compound and what type of bond you had. Earlier, I used the example of sodium chloride, good old-fashioned table salt, what you put on your French fries. Notice the formula, NaCl. Sodium is a metal, okay? Chlorine, which now becomes chloride, is a non-metal. And so by knowing that sodium is a metal and chlorine and chloride is a non-metal, I have a ionic compound. Okay, look at the example of hydrogen, H2O, water. Hydrogen is a non-metal. Oxygen is a non-metal. Okay. When I combine two non-metals, I make the second classified compounds as far as the bonding is called covalent bonding. And there's only 2 types. Either covalent molecular bond, they use that term interchangeably, or ionic. And the main difference is the ionic compounds are made up of a combination of a metal and a non-metal. The covalent molecular compounds are made up of nothing but non-metals. Okay. So to be able to classify it, the type of compound, we need to know what is it, a metal, non-metal. Now, we won't be using a lot of metalloids. We're just demonstrating where they're at. And metalloids, we're not going to be talking much about them, but be aware of where they're at so you can determine whether something is a metal or a non-metal. Okay.
I'm sorry, I have a quick question. I don't really know how to
Sure.
type it.
Go ahead.
So, like, is this staircase thing, is that just coincidence and like how it's like metals and non-metals on like the 2 sides of that staircase, or is something about it make them clump together like that? Like all the non-metals are on one side and all the other. So how does that happen kind of so perfectly, I guess?
Yeah, the answer to that is yes. Yes and no. They fell into that because of the number of protons, but later on we learned that the number of electrons determine whether they have more. This will answer better when we start learning about electrons. But as we move to the right, as we get closer to the gases, remember the gases we just talked about? These are right here, all these gases, noble gases, right? The driving force in any chemical reaction is to be like the noble gases. They're very stable, okay? And they're very stable for a reason, because they have a number of electrons around their structure, which happens to be 8, the magic number 8. The semi-metals, the metals, just by nature of the beast, is they tend to lose electrons, so they end up with a certain charge, a positive charge. The non-metals are like on the cusp. they can act, the semi-metals, I should say, the semi-metals are on the cusp. They can lose electrons with no problem, or they can gain them with no problem. It's like being on the fence. Okay, and that's why they have properties of metals that want to lose electrons, and they have properties of non-metals that want to gain electrons. Okay, so I'm hoping right now, once we learn more about electrons and how they are and how they're placed, the function and why these guys non-metals would come more into play and more be able to see a little bit better. Does that hopefully makes a little more sense to you? It's a function at this point. It's a function of losing and gaining electrons. Okay, because
Okay.
because metals, like I said, semi-metals have properties of metals and properties of non-metals. So they are comfortable with losing or gaining electrons depending on the conditions.
Okay.
All right. Well, yeah, good question. Hopefully it'll come clear. And if it doesn't, when we get to the point, let me know again and we'll work to fix that. All right. So some of the properties of metals. Well, for example, they're very shiny in general. You can stretch them out, you can smack them and flatten them out. And in my other life as a research scientist, I worked a lot with 1/4-inch copper plates, and they were made in Finland. And they started off with a big old block of copper, which is roughly about 3 feet thick, and they were rolled. That block was rolled back and forth, back and forth, back and forth until we brought it down to a 1/4 inch. So they're very malleable properties about metals. All of them are solids except one, mercury. Mercury used to be used a lot in thermostats. It may still be used in some older homes because they conduct electricity. Their density, the density is that ratio of mass over volume. Okay, they tend to be high with respect to density, their value. Their melting points, the temperature in which they become liquid is pretty high. It takes a lot of energy to melt copper metal. To get it, you need a furnace, high temperature. All metals are good conductors of electricity. They conduct electricity, which also means they're good conductors of heat. In general rule of thumb, if you conduct electricity, you will conduct heat. Okay. With respect to nonmetals, they generally have, if they're solids, they have a dull appearance. Okay. If they're solids, also they're brittle. Not all solids, or not all nonmetals are solids. Many of them are gases. Okay. And their density tends to be relatively low. They also have a low melting point. And counter to metals, they're very poor conductors of electricity, and they're much better insulators. Okay. Insulators. Now, looking at the periodic table, obviously for the first 20, be able to name the first 20 in the list that we gave you. Okay. Also, one should be able to be, from slide 35, be given any element and determine whether it is, yeah, we'll talk about that here in a second. The question is, why is gold so non-reactive? And let me finish this because this will be the end of this chapter. And then we'll take a short break. Solid, liquid, and gas. Looking at the periodic table, determine any element. If you're given element number 45, for example, is it a solid, liquid, or gas? Okay, that type of scenario. Again, looking at the periodic table, is it a metal? Is it classified as a metal, non-metal, or a semi-metal? You may see here the term metalloid. It's also another alternative term for semi-metals. And have no fear of ice cold beverage. That tells you which ones are diatomic. Okay, diatomic, again, they are just elements that do not exist by themselves and need to partner up with another one of themselves. Okay. Okay. So that's chapter 1. Now the question was gold. Gold is extremely inert. It's labeled in a noble metal, and it's noble metal like the noble gases are very unreactive. There's something about their structure. There's something about the electrons that prevent. And here's the thing about chemical reactions. All reactions occur on the outer surface, obviously, of the atom, but with the electrons. And if there's any chemical that holds on to electrons a little bit tighter than something else, then their reactivity is less. Or if that number 8 is fulfilled, they're in a stable state, and it takes vigorous reactions to make it work. Gold is very unreactive, but you can make it react. It just takes vigorous conditions like strong acids, nitric acid, sulfuric acid to get it to react. And it's the nature of how the atoms are put together and how the electrons are, what's the word I want to use at this point in time, how the electrons are not as accessible, that makes it very unreactive as compared to other metals. They're not very readily want to give up electrons, because metals, put this in long-term memory, all metals want to lose electrons. All nonmetals gain electrons. Okay. And the result is, keep this in mind, think about it. All electrons have a negative charge. So if I lose electrons, what is my net charge? Would it be positive or negative? From a mathematical standpoint, what do you think it would be? Or put it in a psychological standpoint. If you're a negative person and you lose negativity, don't you become more what?
Positive.
Exactly. Okay.
So like what would metals have to gain by losing electrons? Like what does becoming more positive do for them?
Well, by losing electrons, the next layer, when we start talking about how these electrons are put together, they're not arbitrarily, these electrons in our model are not arbitrarily just thrown in the element. They are in certain levels, energy levels, okay? And by losing electrons, then the next energy level that is down is full, okay?
Okay.
And so it's full, their electron, it's like layers of an onion. Think of it as layers of an onion. These electrons exist at energy levels. And as I build my atom up, fill up each layer, and then I go to the next one, and then eventually I fill that up and I go to the next one. So if I take electrons out from the outer layer and I go to the next layer in, that's full and it's happy. Nonmetals are the opposite. They have empty orbitals on the outside. We call those orbitals. They tend to gain electrons to fill that orbital up, okay? So it's a matter of losing, gaining electrons to fulfill that magic 8, what we call the octet rule. And metals rather give them up and pick it up.
Okay. And so that rule of 8, is it just like ending in an 8 is what they want, or be like just adding 8s to it? Like how does that 8 thing really work?
Well, the 8 is the number 8, number of electrons. They're striving to obtain 8 electrons in the outermost shell.
Okay.
Yeah, the number 8. So you're going to lose or gain electrons. And when we get to that, hopefully it'll come clearer, because you will be able to tell. Remember, I may mention of that the group on top of the column. I said 1A, 2A, all the way across to 8A. The noble gas in group 8A. That 8 represents 8 electrons on the outer, with the exception of helium, it has 2. It has a duet. But we'll get to that. It'll come clearer as we get to it. Okay.
Okay.
Tell you
Thank
what.
you.
Yeah, no problem. Let's take a 10-minute quick break. And what I'll do is I'll start chapter 2 with that. Okay. Let's go back at, I got 2:13 on my clock. Come back at 2:23. Okay, guys, I'm back. All right. Well, the first chapter we kind of gave you a basic introduction to chemistry, and we'll definitely will come back to that. But what we got to do for the next two chapters, this one and three, we're gonna deal with some math. And as I mentioned, may or may not have mentioned, when we talk about math, we're not doing anything sophisticated. We're not doing matrix algebra, any differential equations, and nothing of the sort. Very basic, uh, simple algebra, and math as far as adding, subtracting, and dividing and multiplying. That's about it. Okay. Now, you will need a calculator that will do scientific notation. And all that is a means to input into your calculator big numbers or very tiny numbers, but we'll get to that here in a bit. Okay. So there's on the course website, there's some practice problems. With math, it's always a good practice to do as much as possible that does get more confidence in doing the calculations. And I'm going to be talking about doing these calculations when we get to conversion, doing them in a specific manner, because we're going to utilize that technique when we get back into chemistry and we talk about chemical reactions. Okay. And we set it up properly. Now, when it comes to measurements, obviously we got to have units, because if we measure something like we say the book weighs 8, that doesn't mean anything to us, because are we talking ounces, pounds, tons? We got to have units. So units are very important here. So make sure that when you present your data that you do present it with units, so we know what we're talking about. Every measurement that you do, be it length, mass, weight, has a degree of uncertainty. Okay. And that last digit that you're going to present always has a degree. It's an estimate. Now, it could be such that you may read it a certain number and I may read it a certain number. Neither one of us is correct. That's what you read, because there's a degree of uncertainty. The point of all that is that when you present your data, if you take units, numbers, values that you have measured, okay, and you, let's say, measure something with a ruler, and maybe you measure something else with maybe a laser beam, and you take the results of those numbers, the data you present should not be more accurate than the least accurate measurement, okay? And that's this whole point that we're going to be talking about significant figures and so forth, okay? Yes, you plug in numbers in a calculator to get 30 digits. You might be tempted to report all those 30 digits. That would be incorrect, because you weren't that accurate in your measurement. Okay, length. Well, the units that we use for length, obviously we use in a metric system. We use centimeters, millimeters, meters, kilometers, and I have a table for you here. I sent the table to everybody, how to use the centimeter, decimeter, how to put it all together for you. I'll talk about that here after we're done with this chapter. Okay. Now, here's what I meant by accuracy, as far as being able to do a calculation. So obviously here, the white one is least accurate, right? Because there's less increments here. And so the bottom one with more increments, we can get a more accurate reading with the bottom ruler. And then if we have a different type of ruler, we can get even more accurate. But if I were to take these two measurements and I were to multiply the numbers together, for example, from the white ruler and the brown ruler, I could not present my data more accurate than I get from the white ruler. That's the whole point of presenting your data as accurate as possible, but you cannot be more accurate than the least accurate system that you utilize. Okay. Obviously, the one that has a lot degree of uncertainty is the white one. And if I were to take a measurement of, I don't know, let's call it right, say this point right here, you know, you can see that that white ruler, we're kind of estimating the last digit. And so the white ruler, we can only go to a tenth of a decimal place, whereas the brown ruler, we can go to 2 decimal places. Okay. All right. So mass, what kind of units do we use? Well, mg, lowercase mg, stands for milligram, kg for kilogram, and g for grams. We have two different two balances here. Obviously, the one on the right, if we were actually in the lab doing it, you can see it's very accurate. The digital balance, you can go up to about 3 decimal places with the balance, a digital balance on the right. The one on the left, maybe 2 decimal places. So the digital balance here is a lot more accurate, obviously. When we talk about mass and weight, because we're stuck on Earth, we kind of interchange the two, okay? But there is a difference between mass and weight. And the difference is given as follows. Weight is a function of gravity, okay? We all have constant mass, but depending on your gravitational force, your weight's going to change. And obviously, if somebody weighs 170 pounds here on Earth, we go to the moon, your weight's going to be different because the different gravity. However, the mass remains the same. Okay, mass still stays the same, but the weight is different. Volume. How do we measure units for volume? Well, we use capital L for liter, but we can use the prefix K for kilo and the prefix lowercase m for milli. So milliliters, kiloliters, and so forth. Someone has a question? That is correct. Density is a totally different thing here. Density is that ratio of mass over volume. Okay. It was a question. Here's some types of equipment utilized to measure volume that we were in the lab. Now, for example, units. CC stands for cubic centimeters. Okay. Cubic centimeters. And here's your first conversion factor. 1 milliliter is equivalent to 1 cubic centimeter. So obviously, 1,000 milliliters will be equivalent to 1,000 cubic centimeters. Okay. We're going to be converting from English to metric. We're going to be converting within metric and within English and then cross from each other. So this little tool may help you out with respect to gallons, quarts, pints, and cups. Okay. You can see the big G here for gallon. There are 4 Q's within the G, so that represents 4 quarts per gallon. And within the Q, you have 2 P's, so that represents 2 pints with 1 quart. And finally, within the P, you have 2 C's for cups. There are 2 cups in a pint, okay? 2 pints in a quart and 4 quarts in a gallon. All of these up here are conversion factors that we're going to utilize, and we're going to be talking about those here in a bit. But that we can set those up as a ratio. We can put gallons on top, gallons in numerator, quarts in the denominator, or vice versa. This is no different of saying you're working $50 per hour. That's a ratio, $50 per hour or hour per dollar. Traveling 100 miles per hour, 100 on top per hour, 100 miles per hour, or vice, invert it, hour and 100 miles in the bottom. I'll give you some examples here in a bit, okay? All right, now, sometimes you're given in the lab and you're given maybe in the lecture part, you're asked to measure a liquid. Now, in measuring any liquid, be aware of your starting point. Okay, if we look at the cylinder here, this cylinder is what we call a graduated cylinder. Notice that the 0 point is down at the bottom. Okay, so you're going from 0 all the way up to 25. So that number you're going to read is going to be what, 21 something. and not the other way, not the other directions. Make sure you're reading it correctly. Second thing is this: liquids in the cylinders form what's called a meniscus. They form a concave shape. Okay. When you read a meniscus, you read at the bottom of the meniscus here. So this is the reading, whatever that reading may be. Okay, so it could be like 21, maybe 0.5. You may see 0.4, maybe I see 0.5. We're both correct. It's just that last one always has a degree of uncertainty. There's no measurement out there that is 100%. Okay, there's a degree of uncertainty in everything that we measure. Which brings us to the point with respect to what are called significant figures. Now, the term significant figures deals with whether that digit is significant with respect to some mathematical function that I'm going to do. Okay. It doesn't mean that it's not significant, that it's not worth any value. Okay. Notice the difference there. We're talking about determining how many significant figures we have so that we can present our data with the correct significant figures. Okay. All right. So as the previous example, we got two rulers here. You can see here that we got a difference that is more accurate with the bottom. Okay. And if we were to take these two numbers and multiply them with each other, we couldn't be any more accurate than the one on top, which can only take us through one decimal point. All right, so let's talk about how do we define what is significant, what is not. I'm going to give you the rules that they give you in the textbook, and then I'm going to shorten it for you. And just a simple 2 questions you had to ask yourself, at least for zeros, because the problem is not the integers. Every number from 1 through 9, all integers count. Okay, so this number 4,895.2 has 5 sig figs, all integers. Where the problem comes in and the confusion comes in is the zeros. Now, the rule states that any leading zero, in this case 0.0005454, that they don't count. All they do is just hold the decimal place. So they're not being counted as being significant. Okay, we'll come back to that in a second. The other example of a zero is when they are captive. If a zero is captive between 2 integers, then they are counted and treated as being significant. Okay. So the number 3050 has 3 sig figs. The next number 0.002001. The first 3 zeros are leading zeros. So as per rule number 2, they're not counted. And then the other 2 zeros that are stuck between the 2 and a 1 are captive zeros and therefore count. So that number has 4 sig figs. Okay. And then trailing zeros. Okay. If a zero has a decimal point anywhere in that number and it follows an integer, it counts. So for example, 0.0880. The first 2 zeros ask the question. For the first 2 zeros, which are leading zeros that we know based on rule number 2, don't count. But if you forget, ask the question for the first 2 zeros. Is there an integer in front of those 2 zeros? If the answer is no, they don't count. The answer is no. So the first 2 zeros don't count. Okay. So go to the last zero, the one after the 8. Is there an integer before that last zero? Answer is yes. Second question, is there a decimal point anywhere in that number? Answer is yes. I get 2 yeses, the last zero counts. So therefore I have 3 sig figs. Okay. Do the same scenario for 28,500 for those last 2 zeros. Is there an integer in front of those zeros? Yes is the answer. Now the second question, is there a decimal point anywhere in that number? The answer is no. Therefore, those zeros in 28,500 do not count as being significant. It will not play a factor in determining my final answer with the correct number of sig figs. Now, if I take that same number, 28500.0, can anybody tell me how many sig figs do I have there? 3? No. The number I just wrote, 28500.0. How many sig figs do I have in that number? 4? No. 6 is correct. Okay. Ask the question. Okay. For any of these zeros, I'm just going to put that arrow there. Ask the question for any of those zeros. Is there an integer in front of any of those zeros? Answer is yes. Okay. Second question. Is there a decimal point anywhere in that number? Answer is yes. Therefore, those zeros count. So we have a total of 6, the 285 and the 3 zeros, they have 6. This has 6 sig figs. If you do the same thing, same questions for these zeros, you get no as an answer. Is there an integer in front of those 2 zeros? Yes. Is there a decimal point anywhere in that number? Answer is no. Therefore, those 2 zeros do not count in the 28500. The point being, the moment you put a decimal point, okay, into the number, the zeros, all the zeros count. If they are in front, if there's an integer in front of those zeros, okay? Obviously, these guys right here are leading zeros, and they would never have an integer in front of them. These 3 zeros right there. If you put an integer in front of those 3 zeros, then you change the number completely, okay? So that's basically the question you ask yourself if you forget whether it counts or not with respect to zeros, because we know numbers 1 through 9 count. They count as being significant. When it gets to the zeros, ask those two questions. Is there an integer in front of the zeros? Okay. And is there a decimal point anywhere in that number? If you get yes to both those questions, then those zeros count. If you get no to any of those two questions, then those zeros do not count. Okay. Because we're going to need to know that when we start doing calculations, because especially when we multiply and divide, we're going to be dependent on how many sig figs. Our answer is going to be dependent on how many sig figs the numbers have that they do their mathematical function. Now, there are what are called exact numbers. Okay. These numbers play no factor with respect to sig figs because they are exact numbers. For example, you say there's 14 people. That's an exact number. The conversion factor, 3 feet per yard. Again, it's an exact number. 3 is an exact number. It's not 3.1. It's not 2.9. It is exactly 3. 100 pennies per dollar, 5 pods or 12 pack. Those are exact numbers. And therefore, being exact numbers, they don't count with respect to being used to determine whether they are significant figures. That they aren't, when they say here is not something measured, I'm not measuring the length, the weight, or the height on that. I'm counting, but I'm not measuring. Okay. Things that are measured are not exact numbers. So 7 inches, 200 pounds, 10 ounces, those are measured numbers. Therefore, they would be a factor if I use those numbers with respect to any mathematical function that I do with them later on down the road. So anything measured is not exact. Okay. So sig fig rules don't apply to exact numbers. Okay, let's take this example here. 5.05. How many sig figs do we have here? What we got here? I got 1 and 3. 3 sig figs. Okay. 3 sig figs, 5.05. First of all, the 0, for example, is a captive 0. So using that rule, it counts. Okay. But if we forgot about that, ask those 2 questions again for that 0. Is there an integer in front of that 0? Yes. Is there a decimal point anywhere in that number? Yes. Therefore, I have 3 sig figs. Okay. 1200. Again, ask the same question here for that 0. We get 2. You're correct. Okay. What about this one? 0.02020. Okay. We got 4. That's correct. 4 for that one. Same rules apply. The simple rule for the 0 between the 2's is captive. But again, ask the same questions and you'll get yes for both those 0s. The 0 that is captive and the 0 after the last 2. The first 2, they're leading 0s. But again, you can ask the question, you get a no for no integer in front of them. So they wouldn't count. What about 0.0051? Exactly. Exactly. And 51. Okay. And the moment we hit a decimal point, about 50.00, not 2 for 50, only 1 for 50. And for 50.00, 4. Okay. And then obviously 123.45, those are all integers, so they count. All of them. And then finally the last one, 80, 90. We got 3 exactly. Okay. So we need to learn to determine this because, like I said, when we multiply and divide numbers, we are governed. The answer is governed by, as far as sig figs to present, is governed by that number with the least sig figs. So if I were to multiply, say, the first 2 numbers with each other or divide, my answer should not have more than 2 sig figs because the 1200 milliliters is the number with the least accuracy. That's the drive. You cannot present your data more accurate than that number that has the least accuracy. All right, so this flow chart kind of summarizes there for you. I'll let you read that again, but basically it's the same question, the same thing about the 0s. The trouble part is the 0s. People tend to forget significant or not, but if you ask those 2 questions, I don't think you have a problem. Okay. Well, as I stated, you get 2 numbers, you multiply, you get this humongous number. You don't present that humongous number. You got to truncate it. You got to know where to truncate it and how to truncate it. And so we got to round it. Okay. And so the rule is very simple. We're going to use a simple rule that you look at the number that you're gonna truncate. You're gonna look at the number. So any number to the right of that, you're gonna get rid of, but you gotta have to determine that number that you're looking at. Do I keep it the same or do I boost it up 1 value? And that's what we talk about rounding. We look at the neighbor. Okay. And so we take the number 5.4. I want to round it to 1 sig fig. So I will need to get rid of the 0.4, but I need to determine whether that 5 stays 5 or goes up to 6. So I look at the neighbor, which is 4. It is less than 5. Therefore, I keep 5 as 5. When it comes to rounding, the number that you're looking at either stays the same or goes up. It doesn't go down. You don't bring it down. Either stays the same value or goes up to the next value. Okay. If the neighbor is equal to 5 or more, then that 5 then gets boosted up to the next value. So 5.5 gets rounded up to 6. Okay. The thing to remember is we don't want to change the magnitude. And what do we mean by the magnitude? Well, let's take a look at the number down here at the bottom. Okay. First of all, you can see that we're talking about 5,400. We want to round that number to one digit. So we identified the first significant figure position, which is the 5. So I need to truncate anything to the right of that 5. Now, if all numbers in, let me restate this. First, look at the magnitude. You are in the 5,000 range, okay? And so your answer after you round it should remain in the 5,000 range. You don't want to change the magnitude. So here we're going to round it to 1 sig fig. So we use the rounding rules. We look at the neighbor. 4 is less than 5. So at 5 remains 5. Now, that doesn't mean to drop all the zeros and give you 5. What happens is you take that 4 and change it to 0. Okay, remember, you're in the 5,000 magnitude range. By dropping everything, all the zeros, all those values after 5, you change the magnitude. What do you want? $5,000 or $5? Okay, it's a big difference. And the thing to maybe to refresh is this. The numbers in front of the decimal point get converted to 0. The numbers after the decimal point, okay, the decimal point would be right here, okay? So any numbers after the decimal point get dropped off. You can truncate them, get rid of them. But the numbers before the decimal point, don't drop them off. You change into zeros. Because if you drop them off, you change the magnitude. So always look at the magnitude. Am I in the thousands place, and hundreds, tens, whatever the case may be, because your answer should remain in the same magnitude. Okay. Here's some problems that are asking you to round the numbers to 3 sig figs. Well, to do that, we need to first determine the 3 sig fig position. Okay, so starting from the far left and moving to the right, we determine that the 3 is in the 3 significant figure position. That means that everything else gets truncated. So we look at the neighbor, and that tells us whether that 3 stays 3 or goes up to 4. Okay, in this case, it's greater than or equal to 5. Therefore, the 3 gets bumped up to 4. So we have the answer is 1.84 centimeters. And this is what we're talking about. You don't want to be more accurate than the least accurate number that you started out, because this whole thing here, this answer of 1.834, 1.8374, you may have obtained that while you did some calculation, and one of the numbers in the calculation, multiply or divide, only had 3 sig figs. So you can't be more accurate than 3 sig figs. Okay. All right. So let's try another one. Find the 3 sig fig position. This would be the 6. Okay. And here's an example. You are in the 7,000 range, in the 7,000 magnitude. All right. So then you look, we got the 6. Do we raise it up, or do we keep it the same? We look at the neighbor. All right. The neighbor is 2, is less than 5. So the 6 remains 6. Also keep note that it's a number, the numbers before the decimal point get changed to 0, and anything after the decimal point gets changed, gets dropped. Okay. And so we get 7,160, not 7,016, or excuse me, 716. Okay. By not converting that 2 to 0, you change magnitude. Now, what would be wrong if taking that same scenario and did this? What if I would have presented the number as 7160.00? Okay. Would it be anything wrong with presenting my number as follows? 7160.00? It would, what would, yeah, it would increase, but what would increase, Kathleen? You're right. Sig figs, exactly. Because by not dropping the numbers after the decimal point and changing them to zeros, I have now created, now I have 1, 2, 3, 4, 5, 6 significant figures. Okay. The problem said keep it at 3 sig figs. Okay. Hopefully you all see that, right? So that would be incorrect. Unless it said to put it in 6 sig figs. All right, let's do one more. We have the leading zeros. Again, leading zeros don't count and that's significant. So we're going to find the 3 sig fig position. And so starting from the first whole number or the number that does count, which is the 1, we count from left to right. That is the first one after the 3. That is the 3 sig fig position. So anything to the right of that, we need to truncate, get rid of. We look at the neighbor, same rules, rounding rules. The 1 remains a 1. So that is our answer. Also here, remember, those are numbers after the decimal point. So we need to drop. If we convert them to zeros, we have increased the number of sig figs. Okay. So don't do that. Same reasoning where we did number 2, if I made it 0.00. And then 24,925. We find the 3 sig fig position, which is the 9 right there. Okay. We look at the neighbor. That tells us whether that 9 remains 9 or goes to next number up 10. Because it's a 2, it stays at 9. So we make it 24,900. Don't forget to convert the 2 and the 5 to zeros because it's before the decimal point. If you didn't do that, then you changed the magnitude. It would be 249 versus 24,900. All right. So when it comes to multiplying and dividing, we are concerned about sig figs. But when it comes to adding and subtracting, we're not worried about sig figs. The only thing we're concerned about is decimal places. Okay. We're still keeping the same principle as far as not being more accurate than the least accurate number. We're just doing it a different way because we know that the more decimal places you have, the more accuracy you have. And so the same scenario here, whether we add and subtract, our answer cannot be more accurate than the least accurate number, which in this case would be the number with the least decimal places. Okay. Note the difference. Nothing to do with sig figs. Don't mix the two up. Multiply and subtract, multiply and divide, significant figures play a factor in your answer. Adding and subtracting, decimal places. Sig figs are not a factor here. Okay. So we get 13.5478 feet, subtract 11.20. Okay. You do the full math. Now, when you do the mathematics, don't truncate beforehand. Take your full number, do the full math. Then when you get your answer at that point, then you put it in the correct number of decimal places. And so our answer here is 2.3478 feet. we can see that 11.20 is the number with the least number of decimal places. And so we have to present our answer with 2 decimal places, which is right there at the 4. We use the rounding rules to determine whether that 4 becomes 5 or it stays at 4. We look at the neighbor like we've been doing. It's a 7 greater than or equal to 5. So 4 becomes 5. And the 7 and 8 get dropped. Okay. If you put a 0 in there, what you've done is you put 4 decimal places, which is again, that is the most accurate 4 decimal places, but your answer cannot have more than the least accurate number, which is the one with 2 decimal places. Okay, so we rounded to 2.35. Don't forget your units. And the point being, again, with adding and subtracting, focus on the decimal places. All right, I can't overemphasize that. Focus on the decimal places when you add and subtract numbers. Okay, don't focus on sig figs, because sig figs don't play a factor here. If you look at the answer, okay, 2.35, which is 3 sig figs, 11.20 has 4 sig figs, and 13.5478 has 6 sig figs. So sig figs, significant figures are not an issue with respect to adding and subtracting. All right, so this is a reminder about your magnitude, 100th place, 10th place, and so 100 and so forth, thousands, 10, 110,000s, etc. All right, with respect to multiplication and division, and your final answer should have the same number of sig figs as the number with the least sig figs. All right, so we have the number here, 3.546 times 1.4. Okay, which number here has the least number of sig figs? The 1.4, exactly. Therefore, our answer should not have more than 2 sig figs. Okay, but don't truncate anything. Do the full math, and then truncate as needed. So, doing the full math, our answer is 4.9644. Since our least significant, least accurate number was 1.4 with 2 sig figs, we need to go to the 2 sig fig position, which is the 9. Okay, and then determine whether that 9 goes up to 10 or it stays at 9. We do again as normal, like we've been doing, nothing's different. We look at the neighbor, which is 6, is greater than or equal to 5. Therefore, 9 becomes 10. We carry the 1. Our answer is 5.0. Note the units. And here's a refresher on units. Okay, we have M times M becomes M squared. If this was a plus, let's say we're adding a number, and then it would just be M, right? But we're multiplying. And so it becomes M squared. And if we were to multiply a third one, it would be M cubed. Okay. So with respect to multiplying, is it 5.0? Yeah, because 0, yeah. Well, it's 5.0 because that 9 gets pushed up to 10, and you have to carry the 1. Okay, so it's 5.0. All right. All right. All right, so so focus on sig figs when it comes to multiplication and division. Don't mix up the two. Adding, subtracting, I can't overemphasize this, decimal places. No sig figs. Multiplying and dividing, sig figs only. Okay? Don't cross it over. Which brings us to scientific notation, because we will be doing calculations with humongous numbers, either very big or extremely small. So scientific notation is a means to present these numbers. Okay. The mathematics is the same. It's just that we're going to either multiply or divide with humongous numbers. It's just you have to have a means to one, put it into your calculator and to present them. For example, let's take approximately the distance from the Earth to the Sun is roughly 93 million miles. Okay. We want to put this in scientific notation. Well, step number one, we first determine how many sig figs we have in that number, because when we put it in scientific notation, we have to put it with the correct number of sig figs. So 93 million miles has 2 sig figs. Okay. Our answer in scientific notation should display 2 significant figures. Now, how do we do this? Well, first thing to look at is that this is a number which is much greater than 1. Okay, and so our decimal point would be right there if we were to use a decimal point, correct? Okay, so starting from where the decimal point will be, we count from right to left. We move the decimal point over until we find the last integer, and we stop before the last integer. In this case is the 9. So we count the positions from the decimal point to the front of the last integer, which would be the 9, and that is 7 decimal places. So that decimal point now is 9.3 times 10 to the 7th power. Okay. Now, some people are confused with this and say, what times 10 to the 7th power? What does that mean? Well, I'll tell you what it means. It's just another way to write this. 9.3 times 10 . 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, did I go too far? Not 10, 7. 1, 2, 3, 4, 5, 6, 7. This should be 7 right there. Okay. 1, 2, 3, 4, 5, 6, 7. And so that's just another way to write 9, to write that number is simply what I'm doing is taking 9.3 and multiplying it by 10 7 times. Okay. And I can combine those 10s because if we got an exponent of 1, when I multiply 10 to the 1, I just add the exponents and I got 7 10s. Like 10 to the 7th power. All right. Now you might be tempted to stop before the last integer. Don't do that. That is not the correct scientific notation. That number listed here, 93 times 10 to the 6. Yes, that is 93 million. However, it is not in the correct scientific notation format. There's always an integer up front by itself, followed by the decimal point. The other aspect about scientific notation is that if you ever have to write a number with the correct sig figs and it's a kind of ambiguous, you can always put it into scientific notation, because scientific notation will always be in the correct significant figure format. Okay, I'll give you an example of that here in a bit. All right, so the other direction is very small numbers. Okay, now notice the previous example, the exponent 10 to the 7th is positive number. So this is $93 million is a positive number. When we have very, very tiny numbers, and this time we're moving the decimal point from left to right. we do the same process. We find the decimal point, which obviously is right here, and we move it over until we find the first integer, and then we put that decimal point right after the integer. We also look to see first is how many sig figs we have in that number, because again, our answer should have the same number of sig figs as we started off with in scientific notation format. So this number has 2 sig figs. Remember, those are leading zeros and they don't count. And so we start moving the decimal point and we move it across, and it is 10 positions. So we get that right after the first decimal number integer, 1. So we write that as 1.7 times 10 to the negative 10. Negative 10 tells me it's a number much less than 1. Now, this is nothing more than another way to write 1.7 divided by 10 times 10 times 10, and etc. I'll let you write the rest of it. It's all you're doing, taking 10 times and taking 1.7 and dividing it. Okay. And so this is how we write very small numbers in scientific notation. 10 to the negative 10 tells us it's a number much less than 1. All right. Well, first problem here is asking you to convert these numbers to scientific notation. The step in any of this is to first determine how many sig figs you have, because you want to be able to, you need to put that number with the correct sig figs. Okay. Hold on 1 second. I got to do something real quick. Something came up. Bear with me. Okay, my apologies. I'm back. Okay. It's a bad time to favorite math class. Well, so did I. Let me tell you that I didn't do very good. I didn't do very good in math either. But we're not going to, like I said, we're not doing complicated math here. Okay. Anyway, so here we're going to convert these numbers to scientific notation. Okay. The step number 1 is first determine how many sig figs each number has. We can see here that the first number has 1, 2, 3, 4, 5, 6 significant figures. Everybody see that? Okay. The second one has 3 sig figs. The third one has 3 sig figs. And the last one has 1 sig fig. Okay. And so once we know that, we got to make sure that we present the number in scientific notation with the same number of sig figs. All right. So with that in mind, this is what we got. So we find the decimal point. I'll give you the answer and then we'll walk it through. Here's the decimal point, obviously, right? Well, and it's a number greater than 1, so our exponent is going to be positive. So from the decimal point, we move from right to left until we find where we stop in front of the last integer, which is the 5. That's 2 positions. So moving the decimal point over 2 positions to the left, in front of the 5. Now we can write that as 5.48005 times 10 to the 2nd power. Okay. Similar with what we did earlier with the 93 million, this is where the decimal place would be. We come across, we keep going from right to the left. It's a number greater than 1. Obviously, we're going to have a positive exponent. Okay, we stop right before the last integer, which is the 6. We have 3 sig figs. We got to keep 3 sig figs, which is 6.8 times 10 to the 7th power. Don't forget your units. Here, the decimal point is sitting here, and it's a number less than 1. So that gives me a hint and tells me I'm going to have a negative exponent because now I'm going from left to right. Notice the other first 1 and 2 were going from right to left, and that gave us a positive integer. So here we go. We have 3 decimal place. Three sig figs. The 400 part is significant. So we move the decimal point from left to right until we find the first integer, and then we stop right immediately right after it. So the first integer is 4.00, because it has 3 sig figs, times 10 to the negative 4 power. And then 2000, okay? 1 sig figs, decimal point would be right there. We go from right to left, 3 positions. It's 2 times 10 to the 3rd. Now, this is what I mean about if you ever have to write a number with a significant figures that you can't write outright. You can't write it. Let's say, for example, you're asked to write 2000 with 2 sig figs. Well, you can't write it with 2 sig figs. If I were to just say, okay, what if I do this? What if I go 2000, what have I done? I've created 1, 2, 3, 4, 5 sig figs, right? So that won't work. What do? Well, I convert it to scientific notation. 2.0 times 10 to the 3rd is 2000 written with 2 sig figs. If the question says write 2000 with 3 sig figs, okay, no problem. I just add another 0. If it says write it with 10 sig figs, guess what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 2000 with 10 sig figs, okay? And so whenever you're presented with the problem and you can't write it, straight out write it with the correct sig figs, convert it to scientific notation, it will always show the correct number of sig figs, okay? Now your calculator. Some students are having challenges with this. I don't know. I got 3 calculators. There's 3 buttons that normally allows you to input scientific notation. You may have a button like on the far left image here. It's a blue square. It's got a button that says X, 10, and maybe to the X power. Okay. Now that is the scientific notation format for that calculator. Some calculators may have double E letters. Okay, that is the scientific notation for that type of calculator. I've also included my calculator on Windows 10 here. It uses EXP to show scientific notation. Now, in all three cases, the primary function is the scientific notation is a primary function. Some of your calculators may have that, but it's a secondary function. And that means to access it, you got to hit the secondary button. So it might be written like in the left calculator, written in gold down at the bottom of the button. Okay, so double check your manual. So you can walk through how to input scientific notation into your calculator because you will need to insert that into a calculator that can do that because we'll be working with some big numbers. Okay. Now, do not type in the number and then the time symbol and then 10 to the X power. That is not scientific notation. Okay. I repeat, do not type in the number and then hit the time symbol. Okay. And then 10, there is a function by itself, 10 to the X. That's not scientific notation. Not to be confused, the newer ones have a button that says X 10 to the X, maybe something along those lines. The other button to be familiar with is the positive negative button, because sometimes you need to add a negative exponent. Now, each one's a little bit different, obviously. And if we look at the calculator from Windows, it has a button labeled plus/negative. And what that does, it toggles that number you inputted to a negative or positive value. Sometimes the button you have in your calculator, here's the other one in this calculator, that format has a 10 and a minus. Sometimes it just shows a minus in the bracket, and that's a toggle to go back and forth. Okay, so find that button on your calculator because you will need that. And so basically, if you have like the double E button or any of your buttons, so we're going to type in 2.39 times 10 to the 9th. So basically, you type in 2.39, then you hit your button that puts you in the scientific notation format, and then you just need to type in the exponent. You don't need to type in the 10. You just type in the exponent only, okay? Not the 10 part, 10 to the power. One student was having trouble in the example we were doing. They had that button, but for some reason they needed to put their problem into parentheses. I don't know. You might, like I said, we'll run through the example. Bring your calculator around, see if you get the same answer. Okay. Let's go through that and find out, because sometimes you may need to put a bracket around the numbers that you're going to divide or multiply for some reason for that mode. I think there was a mode problem in that calculator. So you might want to read the manual or look it up on the internet if you don't have the manual for your brand or your model. So here's those pictures again for the calculators I have, I'm familiar with, and then the Windows calculator. So let's do this one, okay? All right, and I'm going to do is I'm going to share with you my Windows calculator. And so I'm going to take 2.84 times 10 to the 23rd and divide it by 7.24 times 10 to the 12th, okay? And so I would type in 2, so let me clear it out here and make sure I got nothing else, 2.84. Now, before I type in the rest, the positive negative button, if my number is a negative, this is where I would plug it in, type in my toggle back and forth. Right now, I've inputted negative 2.84, but it's a positive, so I toggle it back. Now at this point, you hit your scientific notation button, whatever it is for your calculator, in this case, EXP for the one I'm using. It puts a letter E. It may put a letter E, depending on your calculator, or it may even give you the the 10 and then a little superscript for your exponent. But on the Windows calculator, you put the letter, it gives you the letter E. And now at this point, you just type in the exponent value, not the times 10, just the exponent value. Okay. Now that format, that is the Windows calculator format for the scientific notation of 2.84 times 10 to the 23rd. Okay. Now you just divide it like you normally would. Any problem? So I'm going to divide that by, notice what Windows did. It put it into long form. So there's the long form of that number. Don't worry about it. You're okay. Nothing's lost. So now I divide it by 7.24 EXP or your scientific notation button, which could be either primary or a secondary function. Then I type in the 12, the exponent, and I hit equal. There's my answer in gigantic format there, right? Well, I wouldn't, I see that number and I'm like, well, that's a big number there. How many, what's my exponent? Well, some calculators have a SCI function. If your number's presented in large format, put it back into scientific notation format. Oh my God, I thought I was sharing the screen. Thank you. Okay, sorry about that. I forgot to hit the square button, the share button. Let me. Okay, does everybody see that? There's my calculator. I'm gonna clear it out. We'll start again. All right. So I'm showing my calculator, and this is the Windows calculator. I repeat. So I'm going to take 2.84. Okay, 2.84. Now, if this was a negative 2.84, then at this point, I would toggle with my negative. In this case, the Windows button is right there, and I can toggle back and forth. Negative, but it's a positive number, so I'm going to leave it at that. Now you select your scientific notation button, either a primary button or a secondary function button. In this case, it's primary EXP. Windows puts the letter E in my readout, and then a +0. At this point, you don't type in the 10, you type in the exponent value, which in this case is 23. And so this is Windows format to describe 2.84 times 10 to the 23rd number, okay? Now your calculator may show the 10 and then put in the exponent 23. Every calculator is a little bit different. All right, so I've inputted the number. Now, if I needed to make that a negative exponent, at this point, I can toggle the positive negative switch. Notice that? How that switches back and forth? Okay, but it's a positive 23, so I'm going to leave it at positive. If it was a negative value, I would use that. Okay. Now I'm going to divide it like I normally would divide, multiply any number. So I hit the divide. I input the next number, 7.24. Hit my scientific notation button. Add my exponent only. Do not put in the 10 part. Just in this case 12. Okay. And then equal. Now I got this big number. All right. And if you're in the scientific notation mode, it would keep it in the scientific notation mode, or it may give you your full answer there like it is in in my calculator. But I want to convert it back to scientific notation. In my case here, I got an F-E button that I click, and I can toggle back and forth to give me the number written longhand, or click it, toggle it back to scientific notation for the Windows calculator. Okay, check that on your calculator if to get it into the format. Otherwise, you got to sit there and count all the zeros. So this is number here. I'm going to copy and paste, and I'm going to go back to the problem. Okay, and so now the answer I received was this. Okay. Now notice that is the format for the Windows calculator. Okay, here's a question. Yeah, online calculators. I'm not familiar with the Wolfman Alpha. I'm not familiar about that online calculators. That'd be fine. Or you can use your Windows if you're on the your laptop. But any calculator that allows you to do scientific notation. Now, be careful this online calculators, because if you are taking an exam and you're doing the lockdown, it's going to toggle back and forth and tell you, oh, okay, you're getting out of the lockdown exam. So you don't want to do it online where you're taking the exam. If you're doing it for your homework or everything else, not a problem. Okay. All right. So that's the answer it gave me. Obviously, I'm not going to report all that because as per sig figs, if we look at the number 2.84 times 10 to the 23rd, it has 3 sig figs. 7.24 times 10 to the 12 has 3 sig figs. So our answer, okay, needs to be truncated. Okay, at the 3.92 for 3 sig figs, and then times 10, and I need to put it in the correct scientific format, times 10 to the 10th power, okay? Because the E plus 10 is not the correct scientific notation format. That is the format for the calculator, okay? Okay, there you go. Christina says she has the double E button. It's a TI-30X and was super cheap. They should be, yeah, you don't need don't need to go out there and buy some $200-300 calculator. I think most calculators, at Walmart and stuff, I'm probably 10-15 bucks. Is that your cost, Christina, for your calculator that has a double E button? Yeah. Okay, yeah, you don't need to go buy anything expensive. Yeah, 15-20 bucks, and heck, you might even find them even cheaper on like Amazon, or maybe even online on Walmart. But you don't need anything fancy. There are some calculators that do all kinds of crazy stuff. That's not necessary unless that's what you want, but you just need something real simple. All right, so the number I get is 3.92 times 10 to the 10th power. 1409 on Amazon. There you go. All right. So practice with your calculator. Be familiar with the function for scientific notation, be it one of those 3 buttons. Like I said, I had a student yesterday having a challenge with the calculator. When they did this problem, they had to put parentheses around the numerator and the denominator to get the answer. If they did not, they get a totally different answer. So I don't know what's going on there. Wasn't familiar with that calculator, but if you have any questions, shoot me a picture of your calculator and I'll look through it and see if I can help you out. Okay. All right. So let me clear this out. Like some calculators will give you an answer like here we got 1.2, 1.2, 3, 4, 5, etc. And then use an 8 in superscript. That's their format to say times 10 to the 8. Yeah, we do round up to 3 sig figs because you're dividing the numerator has 3 sig figs and the denominator has 3 sig figs. So your answer would be in 3 sig fig format. And as I was saying, the number could be written on your screen, calculator screen, with the superscript just 8, like in this example here. But that's not the correct format for scientific notation. You'll have to write that, take that 1.2, 3, 4, 5, 6, 7, 8, 9, and then write in times 10 to the 8th power. Okay. All right. So let me know if you got any problems with that. We can work through it. We'll figure it out. Last part here, we're pretty much finishing up here with this particular chapter. Okay, the percent. This is pretty straightforward. I mean, you're already familiar with the percent. I mean, this whole class, you know that your homework worth a certain percent, your activities, the lab, all worth a certain percent. All right. So we have a total number of points, which is the whole, and then the part, which is the component from each particular part that you want to calculate the percentage. So in this example here, there's a gold ring that has a mass of 239.45 grams, and underwent analysis, and it contains 198.38 grams of pure gold. Question is, what is the percent of this? You know, it's like asking you, all right, you got a 100-point test, you scored 75, what's your percentage? 75%, right? 75 divided by 100 times 100 gives you 75%. This is essentially, it is the same, 198.38 divided by 239.45. Okay, you get this humongous number. Okay, but keeping an eye on your sig figs, you can see that 198.38 has 5 sig figs, 239.45 has 5 sig figs. Therefore, my answer should contain no more than 5 sig figs. And so, like we've been doing, is we find the 5 sig fig position. You go from the far left, which is the 8. 1, 2, 3, 4, and 5. So this is where we're going to truncate. Anything to the right of that, we look at the neighbor, like we've been doing, which is a 1. This tells us that the 8 remains an 8, and so we drop everything to the right of the decimal point. We drop everything, and that gives us an answer of 82.848%. Okay. Now, I can't overemphasize. I know you might be tempted. Why this is more accurate? Yes, your answer is, but it's not correct. Okay. Again, you can't present data that is more accurate than the least accurate digits or values that you have. Okay. All right. So there are the worksheets, and you got everything there to do. What do we got here? 336. Okay, do the worksheets. Okay, tons of work there, and I got to introduce to you my little assistant. Okay. Any questions? She's my little helper here. This is Ruby Rose. She's like, what's going on? All right. Any questions, comments, concerns? What we're going to do is continue with